Welcome. So this week we're going to go ahead and keep talking more about relations and kind of build on this a little bit more. So in our problems, the first one that I want to work with, I labeled them out a little bit more clearly this time in the video. So let's just talk about, suppose that A is equal to the natural numbers and B equals the real numbers. What are the elements of A, B going to look like? Well, if we're just kind of looking at this, we might say that A cross B equals the set, obviously, of little a, little b, such that a is a natural number and r and b is a real number. But what does that really mean? Let's see if we can describe it. So the first number is a non-negative. Second number is any real. So for instance, we could have 0 pi. That would be in A cross B. We could also have 0, 0. That would also be an A cross B because all integers are in here. Now, let's visually think about what this would look like. So if I'm thinking about it, normally we consider that if I had two things, if I did my normal geometric thing where I have my X and Y axis that you've done for Euclidean, what this would essentially look like is I would have a bar for all the values here. This would be at x equals 0. This one would be at x equals 1. This would be at x equals 2, and so forth. So we'd end up taking this and we would just have a whole bunch of vertical bars that go off forever because all we're going to have is have these first elements. So we're just trying to describe what this looks like to get our brains wrapped around this concept a little bit more. So this actually leads me to your first problem I have for you, which is actually I want you then to consider this. And this is not a set. This is the closed interval from 0 to 1, and y is uh, just 1. I should more correctly, if I actually was to do this more correctly, um, this should be a set 1. Now, then what is xy, yx, xx, and yy? What do those look like? And the thing about geometrically, you can do the same thing where you're simply looking at, if I was looking at Euclidean plane, what would that look like to do each of these situations? All right, so there's your first one. You're This kind of leads us on to talk about more about relationships because that's actually all that we've been doing with these cross products is really we're just kind of talking about these Cartesian products is a relationship where a relation is if you have two sets X and Y, we do a relationship on the sets is going to be some subset. So that's going to be something inside them. Now you get a relationship on itself, which is just a subset of it crossed with itself. Um, no, a relationship is typically between two things. You don't have like three things in it's a binary operation. So to kind of get you going a little more on this, way we write this, there's a couple different notations. We're talking about this. We often indicate the pair AB is a relation that A is related to B. And this is exactly what you've actually did way back when you first algebra. The X is related to Y because usually when you're drawing it in terms of some function, you had X was your input and Y was the corresponding output. Now, some ways to do that is A tilde. And if any of you want the LaTeX notation of this thing, by the way, it's just slash sim for similar. Another one that I've also seen is ARB. This is for A is related to B. Both these are very, very common, and there's lots of different relations out there that you've already done and utilized. You just didn't call them relation. So, for example, suppose I have this relation right here. AA AB, BA, AC, and CA. And this is from A to itself. So the way that we often visualize this is actually using what's called a digraph. And what we can do for a digraph is we literally put all the points in there. So a digraph is good when you have A going to itself. So then I just have all my little values, A, B, and C. And then I draw each of these as an arrow where I put the tail of it like this. So I start at A and I go back to A. And this one is going to be A is going to B is going to C is going to B, and C is going to A. And so we have this kind of thing. That's what all these relationships give me is this relationship. That is why graph theory is actually super cool and valuable because all the graphs are is a binary relationship. And they're excellent for showing relationships. In fact, even a lot of data analysis is starting to use graph databases versus the traditional structured databases. So that's why SQL, while it's still out there, is those kind of databases that you can query things are actually being replaced with things like graph databases. And well, there's just a new language that's actually just got approved this week of GQL. So these are things that apply in a lot of different manners, and we can draw the graph to kind of visualize it. All right, so let's talk a little bit more by what if I had this and I want to define it with if it divides. So X, so I'm dividing the relationship divided. So that's what the notation literally means. Well, so what we do is we simply, again, let's put our values, but I'm going to do this kind of funny. I'm going to do 6 here, and then I'm going to do 5 right here. I'm going to do 4 over here and 3 over here. Well, 6 clearly divides 4. I mean, 5 does not divide 6. So actually, let's take that 5. Let's put it over here. But actually, I have my head's wrong because it has to divide it. I'm going to redo this. So I have 6, I have 4, I have 3. Now 3 divides 6 because notice X divides this. We have the arrow pointing from what it does to divides. Then we have 2. Well, it's going to divide 1 and 4, but it doesn't divide 3 and 5. But 1, on the other hand, it divides everything. And then we can do this. And so we can get this kind of relationship where we actually are drawing the visualization of what this looks like. This leads into a concept known as a Hasse diagram, which is often used for the divisors of a certain number. However, it requires that one of the properties of that we have some key properties that we're going to get to in just a second that are in relationships. There are 3 key properties that we look for, and the question is, do they exist, yes or no? All right, so here's what I want you to do. So just like I drew this digraph here, if you were to deal with the relationship on the real numbers where X is related to Y, if X is less than or equal to Y, what kind of picture could I do this in R squared? So think about that. I mean, this is one that because we're dealing with real numbers, I wouldn't recommend a digraph. Is there another kind of graph? Visualize this relationship. All right, so now we get to the key properties I mentioned a little bit ago in the division, the 3 properties, which are reflexive. That's for any X in A, X is related to itself. Reflexive just means it's related to itself. Symmetric means if X is related to Y, then Y is related to X. So all the relationships have to be both ways. Let me give you an example real quick of a relationship that's not symmetric. And I'm going to use a real world example. Symmetric in the relationship of father-son is not symmetric. I am the father to my sons, but they are not the fathers to me. So therefore, that's not a symmetric relationship. Now, if we said blood relation, I am blood related to my children and they're blood related to me. So that would be a symmetric relationship. That's a real world example of that one. Finally, transitive is if X is related to Y and Y is related to Z, then X is related to Z. And these, by the way, are properties that you've already used before in different things and operations that, and you actually did this a little bit as a child. You just don't realize you were doing it. So let's actually apply that by talking about what those look like in terms of an actual graph. So I have a finite set A, and I'm just going to draw a set. I'm going to make some elements. So let's consider A. What does reflexive look like first off? Reflexive means that A is going to go to itself. So the reflexive means that we have loops for every single thing. So if I put a second element out here, B, it is related to itself as well. Now, let's suppose that A is related to B. Then symmetric means that B is related to A. Let me get rid of those loops. I don't need the loops. The loops were only for reflexive. We could have a symmetric relationship like this that is not reflexive, but it is symmetric. Be aware that's possible. And then finally, here's C. So A is related to B and B is related to C. Then the thing that we get as a result is that A has to be related to C. So notice it still is one directional thing. This is something that is really, really nice because and we already did this when we did divisibility. If A divides B and B divides C, then A divides C. You prove that using the definition of divisibility. But this idea of relationships then tells us a little bit more. So we're always checking, is something reflexive, symmetric, or transitive? And we want to know. So with that, I want you then to do this. Suppose you have P people and they're at a party. So you don't actually have a true set here. You're just going to describe what this means, okay? Just like here, I was just trying to describe what that looks like. If it's reflexive, those loops, symmetric, if it goes one way, it comes back. There has to be two-way arrows. And this one, if arrow and then arrow, then we have to have a third path connecting the first and the last. This one, now let's consider what it looks like if I have a group of people at a party where N, you might want to think about this. So N is relationship. So X and Y would be that X knows Y's name. What's it mean to be reflexive? Think about that. Symmetric and transitive. You might also think about which of these are realistic that people actually could have if you pulled a party out. All right. Then I want you to come back and I want you to attempt this. Now, this is where it's going to get kind of funky, is I want you to think through each of these situations. And I've broken them down by, don't worry, there's a second page here, and I'll flip back. So first, let's say P sub T is a relationship of people with accounts on Twitter where T is XTY is that X follows Y on Twitter. Is that reflexive? Is that symmetric? And is that transitive? You need to check each of those three situations and explain why or why not. If it's not true, remember, all you got to do is provide a counterexample. If it is true, you have to explain why it would always be true. Cameron, let's say we have the set of all people, and H, my relationship H, is that X and Y have the same height. Again, is that reflexive, symmetric, or transitive? Alejandro is similar, but now you are doing T where X is taller than Y. Again, is it reflexive, symmetric, or transitive? And Jackson, consider the relationship divides on N. Is divides reflexive, transitive, or symmetric? It could be all three. It could be some combination of them. It could be none of them, to be honest. There are relations that fail all three. So you could have anywhere from zero to all three of these be possible. In the next group, Cameron, you have a set of lines where parallel is your relationship, and they're related if the lines are parallel to each other. Everyone, I'm giving you this one. This one's a little bit harder. C01 is a set of continuous functions on 0 and 1. So we have a function, and we're going to say that f is related to g, where f and g are continuous functions. If the absolute value of the integral of the absolute value of f of x from 0 to 1 is equal to the integral of the absolute value of g of x from 0 to 1. So here's the question. Are they going to be reflexive, symmetric, and transitive? Think about that for a second. Can they both have f's on both sides? And if f is equal to g, does g equal f? And so forth and so on. We have all these things we kind of work through. Then Alejandro, you have this one where n is related to m if n plus m is even on the natural numbers. And finally, last, I want all of you to try D, where on the relationship real numbers, where x is related to y if x equals 2y for any, and remember, that doesn't mean that they all have to be related. You could have two numbers that aren't related, but suppose that you have to, so going back here, we start with suppose that x is an element of y, x is related to y. Boom. That's the question. Is every x related to every y? Yes or no? For parts B and C, there's an if part. You have to make sure the if part's true. Then we have to get the then part. So that's the key thing to remember here, that this is applying logic to test out every single one of these situations. But wait, I'm not done. We got a little more. And that's going to come in your other video this week because we're going to keep diving into this. So make sure you jump in, get these problems done, and let me know what questions you have.